Oh wait, that's not really what I wanted. I really wanted this to say for x greater than, actually I want to split these up at 1. So I meant to do that. Okay, there we go. So if we're talking about where this function is continuous, kind of that first line of defense for continuity is to think about the domain of the function. So because we have a piecewise function, I have to think about the domain for each of these pieces. So for this second part, 2x plus 1, that's a line. So if I only had the function y equals 2x plus 1, the domain would be all real numbers. When I look at this part, 3 over x minus 2, if I'm thinking about this in terms of domain, this piece for domain, I know this piece, domain-wise, says x cannot be equal to 2. So I just want to we're going to keep that in mind as we address the continuity piece. So already I know that it is not continuous at x equals 2. But because it's a piecewise function, I also have to think about, is it continuous at the x value where it's matching up? And here, the x value where my two pieces are matching up is 1. So I'm going to check our 3-part definition of continuity at x equals 1. At x equals 1, I need to know, does f of 1 exist? Well, that says, look at our function. Is there somewhere with that or equal to that's going to let me actually plug in the 1? And there is. So here, if I take the 1, and this is the function I'd get to plug it into. So I'd have 2 times 1 plus 1, and I'd get 3. So far, so good. That next piece for our definition of continuity, I know that I need the limit from the left and the limit from the right to match up. So if I look at the limit as x approaches 1, as x approaches 1 from the left, or 1 minus a little bit, if I'm at 1 minus a little bit, this is the part of the function that we would be looking at. So I'm going to have 2x plus 1. And the question is that equal to what we get when we look for the limit as x approaches 1 from the right-hand side, or 1 plus a little bit? And for the 1 plus a little bit, this is the part of the function we'd look at. X minus 2. What do we do when we see a limit problem? We try plugging the value in. So if I plug in the 1, 2 times 1 plus 1, I get 3 over here. And the question, is that the same? When I plug in 1 over here, I get 3 over 1 minus 2. So I get 3 over negative 1, or negative 3. They're not equal. When I go to write the domain, so that's enough to know this is not continuous at x equals 1. So when I go to write the interval where this is continuous, I know that I have to leave out 1 and also leave out 2 because of our domain issue with this part of the function. So the intervals where it is continuous, so f of x is continuous from negative infinity to 1, union from 1 to 2, union from 2 to infinity. So I'm just punching out the hole at 1 and punching out the hole at 2. So if I'm looking for the intervals where the function is continuous, the first thing that I need to know is what's the domain of the function. So here, thinking about the domain, x minus 10 is a line, which means the domain is negative infinity to positive infinity. Here, the square root of x minus 4, I can't plug in a value of x that's less than 4 because we get a square root of a negative number. So actually, this one has the most restrictive domain of any of the ones we've done so far. this domain-wise for this piece, I know that x has to be greater than or equal to 4. Or, so I know that this piece of it is only going to be defined from 4 to 13. We could talk about that with a graph in a minute, but really I just want to hold on to this idea that my domain this time is not going to go from negative infinity to positive infinity. This time my domain is only going to go from 4 to infinity. And now we have to check that continuity piece where they're matching up. So first I look at the domain, then I check continuity if it's a piecewise function. So I'm going to check at x equals 13. And at x equals 13, the first thing I want to know, is there somewhere that we get to plug in the 13? And there is, because this one has the or equal to. So I'd have the square root of 13 minus 4. And 13 minus 4, that's going to be the square root of 9 or 3. Great, we got a number. And I guess I feel like 3s today. Next thing I'm going to check is the limit as x approaches 13 from the left. So on the left-hand side of 13, looking at that top function, because this is where x is less than or equal to 13. So I'd have a square root of x minus 4. And I want to know, is that the same as taking the limit as x approaches 13 from the right? Well, the right-hand side of 13, that's going to be this linear function, x minus 10. Over here, what do we do with the limit problem? We try plugging it in. If I try plugging in the 13, 13 minus 4 is a 9, square root of 9 is 3. And we want to know, is that the same as what we get over here? And 13 minus 10 is 3. So they match up. So now we've checked the first part of the continuity definition and the second part of the continuity definition. And the third part of the continuity definition says, is f of 13 equal to the limit as x approaches 13? Oops, not 113, just 13. 13 of f of x. And it is, because we got 3 for that first part and 3 for the second part. So this function is continuous at 13, which means this original domain is also the interval where f of x is continuous. F of x is continuous on 4 to positive infinity. Now, the reason that I wrote these out, and we will definitely do all of these, but I claim that only one of these actually requires a quotient rule. But oftentimes I see students do each of these as a quotient rule. And it's not wrong to do them as a quotient rule, but I am not someone who ever has extra time on a test. I am someone that needs every single minute they're going to give me. So 2 of these don't require a quotient rule, and they're going to be faster to finish if we don't use a quotient rule. So does anyone know which one of these does need a quotient rule?
Number 5.
Totally. That is the only one I'm thinking about that needs a quotient rule. So for both 3 and 4, rather than thinking about this as a quotient rule, for example, this one is equivalent to writing 2/5. That's just a number. That's a fraction, but it's just a number, x to the 5th power. This one right here is equivalent to me saying 5/2 of x to the negative 5th power. This one, I'm kind of stuck with. I have two things in the denominator that are separated by addition or subtraction. So there isn't a nice way to like break that apart into smaller pieces. So let's do the two quick ones, and then we'll do a quotient rule on the last one. And I wrote all these, but the truth is I'm gonna need the board space. So if anyone didn't get a chance to do them before, to snap a quick screenshot now. Okay. So here, if I'm going to find that derivative, then it's just a number times x raised to a power. So I'll take that power, multiply it down in front. My 5s will cancel out, and I'll be left with 2x to the 4th power. Here, when I take that derivative, I'm going to multiply that -5 down in front. -5 times +5 will give me -25 over 2. And when we subtract 1 from the exponent, we'll be at -6. As an alternate way to write this, you could also say that that's -25 over 2x to the 6th. Either one of these is full credit, 100%. They're correct. Now this last one, because there isn't a convenient way for us to rewrite this yet, I'm going to need a quotient rule. So when I go to take this derivative, terms of my quotient rule, I'm going to get my pieces going. And if I think about this as an f over g kind of situation, then for my quotient rule, I should have f prime g minus fg prime, and on the bottom, a g squared. So I'm going to fill in my pieces. So here, I'm going to leave g alone and have 5 plus 2x. F prime, so I'm taking the derivative of 1, and the derivative of a constant is 0. Here, we'll leave the f alone and then take the derivative of g. And the derivative of g here, 5 plus 2x, when I take that derivative, I'll have 0 plus 2. And in the denominator, we will leave the g alone. We could decide to simplify this. Certainly over here, 0 times anything, that's going away. And this is going to end up being 1 times 2. So on the top, I've got 0 minus 2. I'll squeeze it in down here. So my f prime of x became -2. And then in the denominator, 5 plus 2x squared. And that would be my final answer there. I do want to say that this one right here, recognizing that we can rewrite this, this is the one thing that I really think is going to save you a bunch of time. And sometimes it's easier to recognize when we have numbers on both the top and the bottom. Sometimes it's hard to train your brain to not see this as a quotient rule. So I'm just going to do a couple more of these where we're going to rewrite things and kind of practice recognizing when I actually need a quotient rule and when I don't. So if I had 3 over x squared, or if I had the square root of x over 4, or if I had x cubed plus 2x over 5x squared. I claim that none of these require a quotient rule. When I walk up to a problem, if I really just have combinations of x's raised to powers, before I go straight into other fancier derivative rules, I'm really going to pause for a second and think about, can I make that look like a number times x raised to a power? On this first one, I can rewrite that to say 3x to the negative 2. Now I just have a number times x raised to a power. Here, I can rewrite that 4 is in the denominator. There isn't a number on top, but that means there's an invisible 1 on top. And I can make this say 1/4 x to the 1/2 power, because that square root tells me that x is raised to the 1/2 power. This one might be a little bit trickier to see. Because I have a single item on a monomial on the bottom, I don't have any addition or subtraction. This I can break apart as 2 separate fractions to say x cubed over 5x squared plus 2x over 5x squared. And then before I take a derivative, I can simplify each of those. So here, when I've got 2 things with the same base, so I can subtract those exponents, and 3 minus 2 is going to leave me with an x to the 1. I also have that 5 in the denominator, which means this is going to be rewritten as 1/5 x. Here, I've got a 2/5 as a fraction, and when I simplify those exponents, I'm going to get x to the negative 1. Now that we did our rewrite, now we're ready to actually take those derivatives. So now I'm going to get that, when I take the derivative here, I'll take that exponent, multiply it by my coefficient out in front, and end up with negative 6x. Subtracting 1 from the exponent, I'll get negative 6x to the negative 3rd. Or if you prefer to rewrite this at the end, that's also negative 6 over x cubed. Again, either one is fine. My next one here, I'm going to take that 1/2, multiply it by 1/4, end up with 1/8 x to b. And when we subtract 1 from a half, we'll get negative 1/2. If we wanted to rewrite this, I could rewrite this because of that negative exponent. I know it's in the denominator, and that 1/2 power tells me it's a square root. So I could rewrite this as 1/8 square root of x. Down here, when I take that derivative, we're going to have 2 pieces to it. The derivative of 1/5 of x, just left with that 1/5. And the derivative here, I'll take the negative 1, multiply it down in front. So I'll have negative 2/5 x to the negative 2. And just like we did on the others, you could choose to rewrite this. And I could say that's 1/5 minus 2 over 5x squared. Okay, here's my function. I've got x squared sine of x. It is not just x's raised to powers. It's kind of a mixture of some algebra-ish stuff and some trig. So this time I am going to have to use the product rule. There's an invisible product here between the x squared and the sine of x. Got this invisible product. So when I go to take the derivative, thinking about that product rule, I know I'm going to have all of my pieces. And for the product rule, this would look like f prime times g plus f times g prime. Now I'm going to plug in all of my pieces. So if I've got that x squared, the derivative of x squared is 2x. I would leave the sine of x alone. My f, I've got an x squared, and now I need the derivative of sine of x, and the derivative of sine of x, you're all going to get memorized. is cosine of x. But let's do more than just find the derivative here. Let's go back and practice something that we were doing last week. And what I would actually like to do is to find the equation for the line tangent to f of x when x equals pi over 2. I mentioned that a lot of the trig stuff we have to get memorized. It's not going away, so just know that we're going to need it for 16a and 16b and 16c if you're hanging out through 16c. If I'm asked to find the equation for a tangent line or any line at all, there are always two things that I need. I need a slope and I need a point. Well, in the original question, I was given half of a point. And the reason I say that is I was only given the x value, not the y value at pi over 2. So to turn that into a point, I need to know what is f of pi over 2. And for now, I'll just write that as f of pi over 2. In terms of the slope, the way that we find the slope of a tangent line, calculus style, is to take the derivative and evaluate it where we care about it. So notation-wise, I could write that that slope is equal to f prime at pi over 2. And then once we have all those numbers, we'll plug them into the y minus y1 equals m times x minus x1 equation. Now for the trig. Let's figure out what f of pi over 2 is. So f of pi over 2 looks like pi over 2 squared times sine of pi over 2. Pi over 2 squared, there's not really a whole lot I can do with that. I could write that as pi squared over 4. But sine of pi over 2 is a number that we should know. And sine of pi over 2 is equal to 1. So our y value when x is pi over 2 is pi squared over 4. And go ahead and put that into our equation now and have y minus pi squared over 4 is equal to, and we'll need to get a slope in a second, but I can do the x minus pi over 2 part. To get our slope, we need to evaluate that derivative at pi over 2. I think I can squeeze it in here. So if I'm finding f prime of pi over 2, then I've got 2 times pi over 2, which would leave me with a pi. Sine of pi over 2, we figured out was equal to 1. Since I've got an x squared, that's another pi squared over 4, because I'm taking pi over 2 times pi over 2. And cosine of pi over 2, another number we should have memorized, is 0. Well, that means that my slope at pi over 2 is just going to be equal to pi. And we can leave the equation like this, or we can rearrange it. Doesn't really matter. I would probably just leave it like this, unless it explicitly told me that I needed it in y equals mx plus b form. Okay, here's my instructions for the next one. For which values of x does f of x have horizontal tangent lines? Before I even tell you what f of x is, I want to make sure that we kind of see the big part of this, and that is if we have horizontal tangent lines, that's the same as asking when is the slope equal to 0. if we're talking about the slope being equal to 0, then calculus style, the way that we find the slope is to take the derivative. So we're looking for where is the derivative equal to 0. And I know I didn't give us a function yet, so let me give us a function. So my function, I'm going to make this f of x is equal to sine of x times cosine of x. We got two things being multiplied together, right? If I called that an f times a g, then I know when I get that derivative, I need my pieces. I need my f prime times g plus my f g prime. So the derivative of sine is cosine. The derivative, and then we're going to leave cosine alone in terms of our formula. So I'll have another cosine there. Over here, I'm going to leave the f alone. So I've got sine of x. And when I take the derivative of cosine, I get negative sine. And then we know that this question asked us, where is that derivative equal to 0? I don't know about you, but this is a little bit messy to look at for me. So if I'm going to try to solve this, I'm going to write this in our nicer notation, which is that if I have cosine times cosine, we can write that as cosine squared x. Here, I've got a positive sign times a negative sign, so it's going to be negative sine squared x. Now you might be thinking, wait, isn't that basically that trig identity we're supposed to have memorized? It's not, because that trig identity has a plus in between. Cosine squared x plus sine squared x would be equal to 1, but we're actually looking for where this is equal to 0. There are a couple of ways that we could get through this, and we could certainly think about some other trig identities, but I've got a better option. I'm going to add the sine of x to the other side so that this looks like cosine squared x is equal to sine squared x. And the reason that I'm doing this is that's going to let me say, well, I can take the square root of both sides, and I know that I have to be careful when I take the square root of both sides because I'd end up with a plus or a minus. So this means that I'm looking for the places where cosine of x is equal to sine of x, or where cosine of x is equal to negative sine of x. Now, if you've got that unit circle memorized or printed out, or you've got your special angles memorized, this should trigger for you, hey, I know the angle where sine and cosine are the same. It's pi over, type a number in the chat. Where are sine and cosine the same? Pi over. Yeah, we got some pi over 4s. Thank you for humoring me. Appreciate it. So pi over 4 is the angle where sine and cosine are the same. So I know that I'm looking for pi over 4, but this also tells me that I'm looking for the places where sine and cosine are the same but opposite signs. So I'm really looking for pi over 4 in all 4 of our quadrants. So pi over 4 in the first quadrant is pi over 4. In the second quadrant, because I'm incrementing by pi over 4s, right, my reference angle is a something over 4. Rather than thinking about this as pi, I'm going to think about it as 4 pi over 4. So if I back up 1, I'd be at 3 pi over 4. If I go forward 1, I'd be at 5 pi over 4. And then my last one, well, if I went all the way around here to 2 pi, but I think about that 2 pi as something over 4, multiplying that guy by 4 over 4, I'd be at 8 pi over 4. And backing off 1, I'm at 7 pi over 4. technically, this is not all of the answers to the question as it is written, because I asked for which values of x does f of x have horizontal tangent lines. These are only the values of x that exist between 0 and 2 pi. But sine and cosine, they keep going on forever. So I keep spinning around the circle as many times as I want. So one of the ways that we sometimes write the entire set of answers would be to do something like x is equal to pi over 4 plus or minus, because we can go in either direction, and the distance between each of these points, right? Each of these are incrementing by 2 pi over 4 or pi over 2. So I could say that x is equal to pi over 4 plus or minus n pi over 2, where n is any number. And really, we often say that n is an integer. And it's equal to t times cosine of t. And I want to find the average rate of change on 0 to pi. Okay, so a couple of things just to point out notation-wise. This notation, that small little e, means t is an element of. Those brackets mean that we're including the 0 and the pi. And because we're talking about t is an element of this, 0 comma pi isn't saying that's a point with an x and a y value. This is saying these are both t values. This is going from t equals 0 to t equals pi. I don't know what a graph of t times cosine of t looks like, but we can answer this question about the average rate of change without a graph, because average rate of change means old school slope. We are looking at a change in y over a change in x, or in this case, we're looking for a change in h over a change in t. So this average rate of change on that interval, sometimes average rate of change is abbreviated as AROC. So my average rate of change here is going to look like h of pi minus h of 0 over pi minus 0. So h of pi, I'm going up to my h function and I'm plugging in pi everywhere that we have a t. So h of pi is going to look like pi cosine of pi, and then minus h of 0. We plug in 0, we'd have 0 times cosine of 0. And then the whole thing is over pi minus 0. If we clean this up a little bit, because we are supposed to know some of these values, cosine of pi is equal to -1. And cosine of 0 is equal to 1, but it doesn't matter because I'm multiplying it by 0. Cosine of pi is -1. So that means in the numerator, I have negative pi, and in the denominator, I have a positive pi, and that's going to simplify to be equal to -1. That was like part A of my question. Now part B of my question, I want to know what the instantaneous velocity is. Instantaneous velocity at t equals 0, t equals pi over 2, and t equals pi. Well, this time we're not looking for the average rate of change or the average velocity. Here, I've asked for the instantaneous velocity, and I swapped out rate of change for velocity. Those two terms are interchangeable for us in 16A. So depending on the context of the problem, we might talk about it as an instantaneous velocity. If this function is a position function, we might talk about it as an instantaneous rate of change if we don't know what that function represents. So here I'm going to say that represents a position, so I want to find the instantaneous velocity. Well, that phrase instantaneous tells me go take the derivative. So my h of t is t times cosine of t, and this is asking me to find h prime of t. I've got multiplication, so I know I need a product rule. And we've had some practice, so I'm just going to go for it. I need the derivative of t, which is 1, times we leave the cosine alone. Then I leave the t alone, and I need the derivative of cosine, which is negative sine of t. Now, rather than with our average rate of change, where I'm looking at 2 points and subtracting things between those 2 points, for the instantaneous rate of change or instantaneous velocity, we're taking our derivative and we're just going to plug in each of those points. So this is secretly 3 questions for the price of 1. So if I want the instantaneous velocity at t equals 0, that's going to look like h prime of 0. So I've got cosine of 0, which is 1, plus 0 times something, we're done. We got a 1. That's my h prime of 0. When I go to find h prime of pi over 2, cosine of pi over 2 is 0. So that piece is gone. And here I'll have pi over 2 for my t. And then sine of pi over 2 is positive 1. And then that minus right there is going to make it a negative. And finally, h prime of pi. I plug in a pi here. Cosine of pi is negative 1. So I've got negative 1 for that front part. Oops, I was writing negative pi, not negative pi, negative 1. And then here, I'm plugging in pi, but sine of pi is 0, and 0 times pi will go to 0. So there we go. That's our full answer to part B. Those are our 3 snapshots of that instantaneous rate of change.